Hello everyone. I hope everyone watching this video is doing well in these difficult times. As a part of the 2020 Virtual RoboSoft conference, I'll be presenting a study on flexible fiber interconnects for soft mechatronics. Before I proceed, I would like to thank the Agency for Science, Technology and Research, as well as the SUTD Digital Manufacturing and Design Center for supporting and funding this work. Highly advanced soft mechatronics and wearable systems are required to undergo large deformations while maintaining stable electrical connections between the components. While some systems can undergo deformations of up to 400%, traditional connectors such as copper traces, copper sheets, and insulated wires are not flexible enough. They add mechanical constraints to the system as shown in the figure by the necking of the stretched dog bone with embedded copper traces. They are also prone to fatigue, delamination, and consequently electromechanical instability over cycles of deformation. Recently, liquid metals like E-GAIN have been used as wires and interconnects for highly intricate stretchable circuits for microelectronic components. However, fabricating soft mechatronics with liquid metals requires extensive material processing, handling of chemicals, and clean room techniques. Commercially available conductive yarns have been used in wearable electronics as well as several elastomeric and fabric-based sensor systems. These threads can easily be integrated either manually or using simple automated fabrication processes. Yarn-based stretchable interconnects can be formed by weaving the yarns on stretchable fabrics. However, weaving results in strain-dependent resistances due to the interaction between the stitch structures. Moreover, stretchable fabrics such as spandex have been shown to add significant constraint to highly deformable substrates such as Ecoflex or Elasticil, the kind that are commonly used in soft robotics. Automated deposition of conductive yarns in soft substrates is challenging due to the bending rigidity of the yarn and out-of-place moments created by bending the yarn. Moreover, soft substrates do not offer heavy anchors to place the yarn or to keep them in position. This presentation entails the design and automated fabrication of conductive yarn-based flexible interconnects or FFI. Through analytical models and experimental validation, it has been shown that the FFI can be robustly integrated with soft mechatronic systems without adding significant mechanical constraints to the system. The proposed FFI design consists of an inextensible conductive thread embedded inside a flexible silicon elastomer pattern as shown in the figure. The conductive thread acts as the electrical core, whereas the elastomer serves a threefold purpose. 1. It provides electrical insulation. 2. It forms a strong chemical bond with silicon-based substrates used in soft mechatronics. And 3. It enables large strains without adding constraints to the soft substrate it is embedded in. To simplify the study, we explore a simple meandering or zigzag pattern in detail. However, FFI or of other flexible patterns can be possible as well, such as horseshoe patterns or serpentine patterns. In order to embed these interconnects in soft substrates, it is essential that they don't add any mechanical constraint or disturb the desired deformations. Hence, it is important to model the maximum strain given by eta max and expected stiffness given by E design as a function of design parameters such as geometry and insulation materials. For this model, we assume isotropic properties along the entire length of the interconnect and neglect out-of-plane deformations during elongation. The figure here shows a single unit of the repeating pattern undergoing elongation when a force P is applied. As the extension increases, the interconnect will stretch towards a straight line configuration and then become stiff as the composite properties become dominated by that of the inextensible thread. Using geometric properties, the maximum elongation, eta max, can be given by this equation. In order to calculate the design stiffness of the interconnect, the Castigliano's energy theorem, which relates the elastic potential energy capital U, force load capital P, and displacement U, is applied on a quarter cell fixed to the axis of symmetry. Upon solving the energy theorem, the effective modulus given by E design is given in the equation on the right. Here, AP refers to the cross-section area, E and G are Young's modulus and bulk modulus of the insulation materials respectively, and I is the moment of inertia. Using these two equations, geometry and insulation materials of the FFI can be chosen to create interconnects which are suitable to be embedded in specific hyperelastic substrates undergoing a desired range of strains. Once the design is complete, the FFI is fabricated using a custom 3D printer shown here. The 3D printer consists of a dual extruder capable of dispensing the insulation material using a compressed air dispensing system, here shown as the silicon extruder, and another extruder capable of layering the conductive yarn using a pole-based automated fiber embedding method developed previously by our group, here shown as the thread extruder. The fabrication consists of 3 steps. First, the guide walls of the flexible pattern are printed using the insulation material by direct ink writing as shown. The rheology of the insulation material is modified to make it more viscous and support layer printing. Once 4 layers of the DIW guide walls are printed, they are cured at 60 degrees. Second, the yarn is laid between the guide walls. As shown in the video, the yarn is held by the guide walls despite the sharp bends. Third, the gap between the guide walls and around the yarn are filled by depositing more of the insulation material. The rheology of this material is modified to make it less viscous so that it flows freely in the gaps. The fabricated fiber interconnect can be seen in the figure shown. Microscopic images of the sections A and B allow us to see the conductive yarn is embedded well inside the insulator material. Cross sections of around 1.5 mm square can be achieved using this method. The scale of the fabrication is, however, limited by the gauge of the dispenser needles as well as the thickness of the yarn. The fabrication proposed is scalable and results in low-cost, reconfigurable interconnects using easily available methods and tools. The conductive yarn interconnects can easily be crimped to traditional connectors like crocodile clips, JST connectors, and so on. To evaluate the electrical and mechanical performances of the FFI, 4 patterns of different wavelength and amplitude were printed. The blue patterns shown here are cast into dog bones of Ecoflex 0030 substrate. The geometries of the 4 patterns can be seen in the table. Using the model developed previously, design modulus E design and the maximum strain eta max for each pattern has been calculated and shown in the table as well. The dog bones were then subject to uniaxial tests. The solid curves in the plot show the experimental stress strain data. The curve in blue shows the experimental data for pure Ecoflex, which is used as a benchmark for the composites. As we can see from the plots, for each pattern there is a range of strain for which the composite behaves almost like pure Ecoflex, thus proving that in this range of strain, it does not constrain the substrate at all. The vertical dotted lines in red, green, cyan and black highlight the predicted strain limit or eta max, after which the yarn would start to constrain the composite. The constraining of the composite happens at strains close to the predicted values of eta max. Pattern D also can be seen to have a strain range of 200%. The thick dashed slopes represent the predicted stiffness or modulus, E designed for the patterns. For all patterns, the predicted stiffness are lower than that of the benchmark or the blue solid curve of pure Ecoflex. To demonstrate the electrical stability of the FFIs, the resistance of the interconnects was measured while the dog bones were subject to cyclic uniaxial loading for 1000 cycles. In each cycle, the dog bone was stretched to 80% of the maximum strain, or eta max. As seen from the figure, the values of resistance measured remain unchanged over the cycles. The inset in the plot shows the variation of resistance and strain over one cycle. Compared to copper wires, conductive threads are limited in their current carrying capacity owing to their large resistance. During tests, it was seen that 2-ply and 3-ply conductive yarns could carry a maximum of 1.2 and 1.5 amperes of current. The conductive yarns heated in excess of 200 degrees while carrying 2 or 2.2 amperes for a period of 10 seconds. To qualitatively compare the electromechanical performance of FFI and conventional copper interconnects, embedded carbon ink-based sensors and interconnect systems were prepared. The resistance of the sensor was measured while the sensor was subject to uniaxial strain in the range of 20 to 250% as shown. The performance of the three tested interconnects can be seen in the table, highlighting the robustness of the FFI when compared to traditional rigid interconnects. The FFI has also been demonstrated with other commonly used sensors such as E-gain and UV-cured ionogels. While the current carrying capacity of the FFI is limited, they offer significant mechanical advantages compared to traditional interconnects. They are ideal for connecting data transmission such as TX-RX systems, sensors, and low-energy actuator components in soft robotics. So to conclude the study and its findings, a new design of conductive fiber-based flexible interconnects has been presented. To support the design, a model was developed to estimate the stiffness and elongation of the interconnects and later verified using systematic experiments. A novel, simple, and inexpensive fabrication method has been presented to produce various kinds of interconnect flexible patterns. The flexible interconnects can be used for embedding within soft mechatronic components for actuation, sensing, and various other applications while also being suitable for use as external flexible cables. Further work would be targeted at studying the effect of interconnect contact on sensing as well as its effect on signal-to-noise ratios. Besides, the effect of metallic coatings on the resistive properties of conductive fibers are also worth investigating. Thank you for watching the presentation. If you have any questions, queries, or comments, please feel free to reach out to us at the contact information listed below.